Okay, Assalamualaikum warahmatullahi wabarakatuh. This time we are going to talk about one paper with title Results of Steel Corrosion Test in Flowing Liquid PBBI at 420 to 600 degrees C after 2000 hours. This paper was published in 2002. Okay, so let's start. The introduction shows us the corrosion issue in ADS system. ADS stands for accelerator driven system. What happened there is steel corrosion caused by eutectic liquid PBBI alloy is a significant problem in ADS system. The eutectic alloy is used as both coolant and target material in that system. So in one side, it is very important because we can use that PBBI or eutectic alloy as a coolant and also target material. However, in other site, it is very corrosive. And then we continue with corrosion in ferritic FSC chromium, iron chromium steel, because this is the common materials that being used in the power plant. Corrosion effects have been reported in ferritic iron chromium steels with material losses in the 100 micrometer range. This occurs between 575 and 750 degrees C after 3,000 hours about of exposure to liquid lead. Solubility and corrosion. Steel components have a solubility in liquid lead in the range of 10 to minus 3 to 0.1 atomic percent at this temperature, the particular temperature. Nickel is an exception with a solubility of 2 atomic percent at 600 in lead, as we can see in this table. Nickel has very high solubility in comparison to other. Aluminum also very high, quite high, but nickel is quite high in PB. However, in bismuth, it is very high. Okay, temperature dependent transport process. Solubilities of materials in liquid lead vary with temperature, leading to transport processes. So it depends on the temperature. The higher temperature, usually we will have more solubility. These processes cause heavy corrosion effects, especially with high flow velocity. So not just in static condition. Using or in the real case where the flow exists, then we will have, or that may accelerate the corrosion or worsen the condition. And then comparison between PB and PBBI alloys. The use of eutectic PBBI alloy instead of pure PB exacerbates corrosion issues. It means that utilization of PBBI increased the corrosion issue. PBBI alloys are significantly more corrosive, as shown in comparative solubility data, this table. Okay, as a continuation of the introduction, early experiments with liquid PB and PBBI show that stable oxide scales on steel surface exist, which are magnetite and iron chromium spinels. These can prevent dissolution if oxygen is dissolved in the liquid metal at concentration around 10 to minus 6 atomic percent. Recent studies on corrosion in stagnant liquid lead highlighted the prevention of corrosion through oxide scale formation. So this scale can prevent the further dissolution. Stable oxide layers form in liquid lead at 550 degrees C with controlled oxygen of about 8 times 10 to minus 6 atomic percent and saturated oxygen concentration 3 times 10 to minus 3 atomic percent. So this range, we will have quite stable oxide layer. And these oxide scales consist of magnetite layer and spinel layer underneath, or what we call iron chromium spinels, with a thickness of about 20 to 30 micrometers after 3000 hours. Over longer time scales, the corrosion process on steel may shift from dissolution to oxidation, posing new challenges. Okay. Alloying steel surface with alloy can promote, so aluminum can promote the formation of protective alumina layer, which grow slowly and prevents extensive oxidation. Experiments on iron chromium alloys containing 8% of aluminum showed alumina scale formation in liquid lead at low oxygen potential. The iron aluminite layers on magnet steel, pre-oxidized before exposure, showed no corrosion in liquid PB17 lithium after 10,000 hours at 450 degrees C. Thermodynamic studies suggest that self-healing of the alumina scale can occur in PB lithium if the kinetics are favorable. Although PBBI temperatures are proposed demo ADS can be kept below 400 degrees C to the low melting point, higher temperatures may occur in certain areas like the beam window or the core. So we can control the system at 400 degrees C, but at certain point, certain areas, it might be higher than that. Experiments in this study extend up to 600 degrees C to account for real energy amplifier condition with high energy fluxes. The influence of bismuth in the alloy was investigated using PBBI alloy, detecting alloy in liquid metal loops in Obnis, Russia. So the objective of this study to investigate the formation and stability of protective oxide layers on steel surfaces under high temperature conditions and how these layers can prevent or mitigate corrosion. Additionally, research explores the potential benefits of alloying steel with alumina to form protective alumina layer that could over enhance corrosion resistance, as we know before that it grows slowly. Okay, let's start with the experiment. So this test using the loop test, the corrosion test setup conducted in two non-isothermal forced lead bismuth loop located in Omnitz, Petersburg, Russia. Both loops include main heater, cooler, hot, and cold section. So because it's a loop, so usually we have hot and cold section. Electromechanical pump, purification system, flow water, and oxygen. As for the test conditions, IPP loop has two test sections with temperature 420 degrees C and 600 degrees C. This might be the low or cold section, and 600 is the hot section. Prometei loop hot test section operates at 550 degrees. Both loops contains approximately 60 liters of liquid PBBI. Temperature control achieved using electrical resistance heater. Oxygen activity in the PBBI is about 10 to minus 6 measured by via electrochemical cells. The key difference between the loops, flow velocity in the IPPE is about 2 meters per second, 4 times higher than the Prometei loop. Corrosion experiments are planned to 5,000 hours, which result analyzed after 2,000 hours. Specimen evaluation, post-exposure specimen were cleaned with 180 degrees C oil to remove PBBI residues. Analysis involved metallurgical examination using SEM EDX on the cross-section of the specimen. This is the table showing us the comparison between IPPE loop and Prometei loop. Okay. So as for the materials used is IC316 1.4970 magnet steel with this, as you can see from the table, composition and the surface treatment. Okay, so as we can see, As for materials, this is this below table showing us the composition of all materials. As we can see that ICN 1.49 materials, or materials A and B, has silicon and also sulfur, and contains high amount of nickel. However, for the manet, it's a low nickel based materials with chromium. Okay, so as for the surface treatment, the surface layer 10 to 100 micrometer was alloyed with aluminum in some specimens. As we can see here, that the surface alloy is conducted on material A1 and B1, ICN 1.49 materials. And there are two methods, aluminum foil or aluminum melt dipping. So the two ways is wrapping aluminum foil around the tube and heating at 1040 degrees C for half hours. However, for hot dipping aluminization, following by annealing. Okay. Hot dipping involves immersing a stainless steel in aluminum melt containing 12% of silicon and annealing at 550 degrees C for half hours. As for the cross-section characterization, figure 1 shows 1.970 materials or B2 after alloying by aluminum foil wrapping. As you can see, the upper part, the iron aluminum of layer form, below that nickel aluminum, and we have nickel aluminum and iron aluminum, and we have the bulk material. So it is alloyed by the aluminum. However, we can see the combination or the formation of iron alloy aluminum, iron aluminum, and nickel aluminum on the surface. As for the figure 2, depicts the cross section of hot dipping, which has 50 micrometer layer of aluminum with 12% of silicon. As we can see, the upper part contain only the aluminum layer without the combination of iron, so on. As for the experimental setup, specimens were stacked together and fixed with an internal rod. The entire arrangement was immersed in the test section. How about the result? AC316 specimen or specimen A1, exposure at 420 degrees C. So you can see here, no surface attack can be observed, and the EDX results show no changes in the steel composition near the surface. Protection: a thin oxide scale likely protected the material from the solution, but cannot be observed clearly. And at exposure at 550 degrees C, this figure shows developed thick oxide scales, as we can see, with a magnetite and spinel zone underneath in some areas, but not homogeneously developed. No dissolution attack was observed, and the components beneath the oxide layer remain unchanged. At 600 degrees C, as you can see here, penetration and erosion occurs. Significant penetration of the BBI, as we can see as a white color here. And also we can see erosion, ablation, as we can see that the surface is not smoothly or evenly, or we can see the effect or the formation of formation of the BBI penetration, and we can see some area the thickness of the layer is very thin in comparison to other area. It shows us or tell us that the erosion occurs. As for the B1 materials, at 420 degrees C, No signs of corrosion were observed, similar to A1. At 550 degrees C, large portion, as we can see here, surface covered by continuous magnetite scale with spinel. So it's very nice that we have protective oxide layer. We have the magnetite and we have the spinel. At 600 degrees C, surface appearance did not change significantly in comparison to 550 degrees C. The precipitation of chromium oxide in the grain boundaries continued, forming a dark network. There is a formation also, however, yeah, it's not homogeneously formed, but we can still see the formation of oxide layer, magnetite, and below that we have the spinel. And we can see also the formation of chromium oxide precipitation that form in the grain boundaries. As for the C1 materials examined at 450 to 550 degrees C only, manganese steel is not intended for high temperatures, as yeah, it's not, so it is not conducted at 600 degrees C. What happened at 420 degrees C is the formation of a protective oxide layer observed with magnetite scale on the top and spinel below the surface. At 550 degrees C, protective oxide scales grew significantly thicker with increased temperature. And as for the A2 and B2, where the aluminum foil wrapping treated for these materials, general corrosion resistance, the specimen including IC A2 and B2 exhibit good corrosion resistance, as we can see, across all tested temperatures up to 600 degrees C. So yeah, it is protected. As we can see at 420, we can see the formation of the layer nicely formed and covered, and also protect the materials. Also the same also with 550 degrees C, no signs of penetration of PBBI. Same with the 600 degrees C. Very nice or homogeneous oxide, homogeneous layer of aluminum formed with no penetration. At 550 and 600 degrees C, pores appear in nickel aluminum interface between the iron aluminum and iron aluminum dissolved region. These pores result from the outward diffusion of iron into the Fa aluminum layer. Specimen B2, the nickel alloy interface layer is dense with no visible signs of corrosion. The iron aluminum layer on the top both specimen A2 and B2 remains intact with its original thickness. So no erosion and no penetration of PBI, no dissolution attack observed. As for the A3 diffusion alloy by aluminum hot dipping, observation at 420 degrees C, severe attack on liquid metal are detected upper part of the aluminum layer after 2000 hours. You can see on the top, the white color is the PBBI. And the lower part of the aluminum layer contains up to 10% of iron with a sharp line marking the original surface. And progression at 550 degrees C, the liquid metal begins to corrode and penetrate even the lower part of the aluminum layer that contains some iron. So it starts to penetrate to the aluminum. At 600 degrees C, the aluminum layer is completely eroded. As we can see that it's become thinner, leaving behind only small protection. This new protective layer consists iron aluminum, which must have formed during the test since it was not present initially. As for the B3, the treatment by aluminum hot dipping, Uh, at 420 degrees C, the layer on B3 shows structure similar to that on specimen A3. Behavior at 400 to 500, the same type of attack occurs as observed in hot dipping 316 specimen A3. As we can see, the layer is eroded and also penetrated by BI. At 600 degrees C, remaining small the diffusion zone loses its protective behavior. This zone contains less than 8 atomic percent aluminum. The liquid metal penetrates on the surface, causing nickel dissolution because it's austenitic steel. Large parts of the tube wall are observed to have disappeared. As we can see, part of the surface has been dissolved or uh, broken and then dissolved into the liquid. As for the summary of the result after 2000 hours of exposure, the ICE 316 original shows sufficient protection, plus is sufficient protection. 450 also sufficient. However, at 600, insufficient protection. Using aluminum wrap, all conditions are sufficiently protected. However, at aluminum hot dip, all the conditions shows insufficient protection. As for the original 1.4970 materials, original materials shows sufficient protection for all temperatures. However, for aluminum wrap, aluminum wrap also shows the same. However, for the aluminum hot dip, shows insufficient for all temperatures. For magnet original, it is at 420 and 550 degrees C shows sufficient protection. As for the discussion, the stable oxide layers as protection, the formation of stable dense oxide layer protects steel from dissolution below 600 degrees C. Maintaining an oxygen concentration in the metal is crucial so that we can be sure that the oxide layer is formed. So as mentioned before, it's about 10 to minus, it's around 10 to minus 6 atomic percent. The behavior of austenitic and martensitic steel. Both type of steel develop protective oxide to prevent the contact with the liquid metal. At 600 degrees C, local disintegration of the scale begins, especially in IC or austenitic materials. In specimen A1, after 2000 hours at 600 degrees C, there is significant penetration of PB, leading to zones with reduced nickel and a bright phase enriched with bismuth. The 1.49 materials does not show the same level of dissolution, likely due to more stable oxide layer. Though the reason for this behavior is not fully understood. However, for magnet steel, the magnet steel maintains a continuous protective oxide layer up to 550 degrees C. Increased exposure time might lead to problems due to thicker oxide layers that we know the phenomenon of peeling bedboards. Corrosion at 600 degrees C is not considered due to insufficient mechanical stability. And alloy formation resistance. Steel with surface alloy formation shows good resistance to dissolution by liquid PBBI up to 600 degrees C. If there is enough aluminum and iron to form iron aluminum at the surface, layer at the surface. Austenitic steel's alloy with aluminum foil wrapping and annealing form 15 micrometer thick iron aluminum layer that is effective in creating a stable alumina barrier. Hot dipping and annealing challenges. Specimen alloy by hot dipping in liquid alloy followed by annealing do not form a stable surface layer. The aluminum layer begins to dissolve at 420 degrees C and mostly gone at 600 degrees C, leaving only thin iron aluminum layer to rest. In specimen B3, this thin barrier fails after 2000 hours at 600 degrees C. Role of aluminum in protective layer formation. The activity of aluminum is crucial for forming stable oxide scales. It must be lowered through aluminum formation to counter dissolution attack. The rapid dissolution of aluminum in PBBI due to high solubility in aluminum means no oxide scale can form, making aluminum compounds necessary at surface for protection. This issue does not arise with pure PB melts, where aluminum solubility is much lower. So in this case, we can see that a PB only materials or liquid PB only or pure PB may give good corrosions or a better corrosion, better condition in terms of corrosion attack. As for conclusion, suitability of original steels without surface alloying are suitable for use in liquid PBBI environments up to 550 degrees C, particularly at oxygen concentration 10 to minus 6 and higher, because it's form better oxide layer protection. Performance of surface alloyed specimen, authentic specimen A2 and B2, which were surface alloyed with aluminum and iron aluminum, show no signs of corrosion even at 600 degrees C. These specimens were protected by a stable thin alumina layer. Challenges with hot dip specimen. The authentic specimen A3 and B3 were not hot dip in aluminum, were hot dip in aluminum and anneal at 500 degrees C, were unable to develop protective oxide scales. For effective protection, the activity of aluminum at the surface in liquid PBB must be low to minimize the dissolution rate of aluminum and allow the formation of oxide scale, which is achieved by iron alumina on the surface. Thank you.